What's up, class? Today we're going to be learning about transformations of graphs. Now, there are two types of transformations. The first type is a rigid transformation, and the second type is a non-rigid transformation. Now, rigid transformations are transformations that do not change the size of our function. It can simply be a horizontal or a vertical shift, or simply a reflection over either the x or the y axis. A non-rigid transformation is one that does change the size of the previous function, but it does not change the overall shape of it. Now, that can either be a shrink or a stretch. Okay, now let's do a couple examples of some rigid transformations. Our original function, just for practicality, is going to be x squared. Y is equal to x squared. Now, we all know this is a parabola that opens up, so let's put the values for it. Now that we got the values for x squared, let's plot this on the graph. Our vertex is going to be at the origin. Then we have -2, 4. We also have 2, 4. We have 4, 16. And -4, 16. Now, once we have this, we just connect the dots. Won't be perfect, of course. And connect the dots going up here. Okay, so what do we have here? We simply have the graph of x squared, a parabola that opens up. Now, let's do some transformations to this parabola. Now, the first two shifts that we're going to go over is going to be a vertical shift up and a vertical shift down. Now, there are some special rules that we can use to streamline this process. So, x squared plus a constant and x squared minus a constant. X squared plus c basically means a shift of x squared c units up. And on the contrary, x squared minus c simply means a shift of x squared c units down. Let's go over this a little bit so it can make a little more sense. Now, the first one we're gonna do is x squared plus 2. We're gonna add 2 to it. Let's actually use the green for this one. Y is going to be equal to x squared plus 2. So the 2 is representing our c. Now, what did we say down here? Down here, we had already said that x squared plus c, in our case right now, our c is 2, simply means a shift of x squared 2 units up. Let's see if this is true. Okay, I have gone ahead and put the outputs to x squared plus 2 on a table so it can make it a little easier to graph it. Now, before we even start graphing this, let's make a note of our vertex for the original function, which was at 0, 0. Now we can start plotting x squared plus 2, which we had already determined was a shift of x squared 2 units up. So let's start. Me personally, I always like to plot my vertex first, so we're going to do that. Our new vertex is at 0, 2. Well, would you look at that? Our new vertex is at 0, 2, which already places it 2 units above the previous vertex. Now let's continue plotting all the dots. We have -2, 6. We have 2, 6. We have 4, 18, which is not on this graph, but will be right up here. And we also have -4, 18. Now we just simply connect the dots like we did with our first equation. Now, what do we see here? We see that by adding 2 to x squared, we took the original graph of x squared and we shifted it up 2 units, which is evident by this green line right here. Now, the next part of our rules said that when we have x squared minus c, we simply take x squared and shift it 2 units down. Let's do another example to see if this is also true. We're gonna use red for this one. So our new equation is gonna be y is equal to x squared minus 2. Now, we can make a little assumption here that we're simply gonna take the graph of x squared and bring it down to units. That's what our rule says, right? X squared equals c units down. Our c in this case is 2, so we're taking it 2 units down. You guys know the drill. We gotta make a new table. It makes everything else easier. You have -4, -2, 0, 2, 4. Now our outputs is going to be at 14, 2, -2, 2, and 14. Now, let's go ahead and graph this. You guys know I like to start at the vertex. Our new vertex, it was going to be at 0, -2. Let me make a note of that before I forget. That's a -2, by the way. And then -2, 2 is going to be one of our points. 2 is also going to be another point. We have -4, 14 is going to be a point. And we have 4, 14 is also another point. All right, once we have all of this, what we're going to do is, once again, connect our dots. And would you look at that? What do we have here? We have a shift of x squared 2 units down, evident by this red line right here. To sum up this part of the video, we can conclude that when we have x squared plus a constant, we shift x squared, the amount that it says, let's say it's 2, is 2 units up. If we have x squared minus 3, we shift x squared down by that constant, which is 3 in this case. Now, in addition to vertical shifts, we also have horizontal shifts, which is simply a movement of the graph left or right. Now, there's a little thing I want you guys to pay close attention to. It can get a little confusing. Now, we do have our original function again, which was x squared. We have the table, we have the graph of it. Now, let's say we have x minus 2 squared. Now, obviously we already talked about the vertical shift, so you guys probably are guessing that this is going to be a horizontal shift. If you guess horizontal shift, you are correct, but this is where I want you guys to pay really close attention. You guys see this -2, we're talking about horizontal shifts. You guys would probably assume that we're shifting it 2 units to the left. Wrong. We're gonna be taking this and shifting it 2 units to the right. Our new rules state that if we have x minus c squared, this is actually x squared 2 units to the right. Pardon me. C units to the right. Even though we have this -c right here, we take it 2 units to the right. On the contrary, if we have x plus c squared, this is gonna be x squared c units to the left, even though we have a plus sign inside of our parentheses. So we're actually doing the opposite of whatever the sign says. Now let's do a couple examples so we can reinforce this. Okay guys, I have gone ahead, I have created a table for the equation x plus 2 squared, which we already said was a shift on a horizontal axis of x squared 2 units to the left. I have also gone ahead and put the points. I believe this point is at the wrong location. Let's fix that. It should be right over here at -6, 16. Now we connect our dots. Remember, our old vertex was at 0, 0. And now our new vertex is at -2, 0. So essentially, what do we have? We have a shift of x squared 2 units to the left, evident by this graph right here. So our rule does state that when we have x plus c squared, is going to be a shift of x squared, c units to the left. In this case, our c is 2, so we went 2 units to the left. Now, we could do another one real quick for when it's a shift to the right, which will be an equation something like y is equal to x minus 2 squared. Now, I could do the whole table for this, but we're gonna actually do it an easier way. This is the whole point of learning the rules of transformations, so then you don't have to go through the steps of doing all the calculations. What you can do is just take the points from here and move them 2 units to the right. So this one goes 2 units to the right, this one goes 2 units to the right, this one goes 2 units to the right, which will now put it right here. And this one goes 2 units to the right, which will put it right here. Now we just simply connect our dots. Boom. Something like that, right guys? Yeah, I mean, it's not perfect, but now what do we have? We have our new vertex at 2, 0. We could even like do the whole table thing just to prove it. So you guys see, we're gonna actually do it backwards just to show that you could use the rule to have a little shortcut, you know? X, Y. So when our x is 0, let's say our x is 0, that would be 0 minus 2, which is -2. -2 squared will be 4. Where do we have our 0 at? At 0, we're at 4. Now, our next point we could use, let's use the 2. 2 minus 2, 0. 0 squared is always 0. At 2, we're at 0. So I could do the whole table, but you guys see what's going on. As our rules state, when we have x minus c squared, we simply take x squared and move it 2 units to the right, evident by this green line right here. And when we have x plus c squared, we move its c units to the left, evident by this red line right here. Okay guys, the next type of transformations that we have is a reflection. Now this reflection can either be over the x-axis or over the y-axis. Now to showcase this, I am actually going to use a different equation just so it can make the process a little easier. So our new original equation now will be y is equal to 2x. Again guys, keep it simple. X, y, let's draw our table real quick. Okay, now that we have our table, we can simply see that this is a linear equation. Let's draw the graph real quick. Now, this is our new equation. We have the line for it. Now, there are a different set of rules for when we are dealing with reflections. Now, the rules state that when we have negative f of x, we reflect our table or our graph over the x-axis. And when we have y is equal to f of negative x, we reflect our table or our graph over the y-axis. So let's do a few examples to determine if this is true. So the first one we're going to deal with is when we have negative f of x, which is also known as a reflection over the x-axis. We're going to use the equation y is equal to negative 2x. Same thing, we're going to make our table real quick. Okay, let's plot this real quick. So draw our line to connect the points. Essentially, what do we see? When we have y is equal to negative f, which is in our case the 2 represent the f, we have negative f times the x. We simply take our graph and we reflect it over the x-axis. So we already talked about a rigid transformation. That was our vertical shift or horizontal shift or x reflection, y reflection. None of those do any changes to the graph. Now let's talk about a rigid transformation. Now these type of transformations do change the graph. It could either shrink it or it could expand it. Shrink, expand. Let's do a couple examples of these. Okay guys, in order to show this, I have plotted the points of y is equal to x, another linear function. The first thing we're gonna do is make this function bigger. So our first rule states that when we have a constant in front of f of x, it's a vertical stretch or shrink. Now if c is greater than 1, it'll be a stretch. And if a constant is less than 1, it'll be a shrink. Now let's let 2 represent our constant. So our new function will be y is equal to 2x. Okay, let's do the table. You have x here, y here. Okay, instead of just y is equal to x, now we have y is equal to 2x. So 0, 4, 8, 12, 16, and 20. Now let's plot this on a table to see if we really did stretch our graph by 2. 0, 0 stays at 0, 0. 2 is now at 4. 4 now outputs a 8. 6 now outputs a 12. 8 now outputs a 16. And 10 would output a 20, which is up here somewhere. And let's connect this. We could see that our graph got stretched out. So our 10 used to be right here. 10 used to be at 10, 10, but now 10 is at 10, 20, right? So from 10, 10, we're now at 10, 20 up here. So we stretch this graph out. Now, on the contrary, let's say our constant is less than 1, but greater than 0. It has to be greater than 0. So let's say we use 1/2. So our new value would be, our new equation would be y is equal to 1/2 of x. So let's do the same thing again. Plot our table, do our table, put the points down. Now let's plot this on the table, on the graph real quick so to see what happened. 0, 0, we have a point at 2, 1. We have another point at 4, 2. One at 6, 3. One at 8, 4. And just to have it on the table, let's put one at 10, 5. Right? So now, when we're at 10, our y value is only 5. So what do we see? We shrunk our equation down by half. Our graph is now shrunk by half. This is the original graph right here. When we have 2x, which is a vertical stretch because the constant is greater than 1, we enlarge the graph, right? And when we have a constant that is less than 1 but greater than 0, for example 1/2, we shrunk our graph. Now we have gone over a vertical stretch and a vertical shrink. there is also a horizontal stretch and shrink. Now, I need you guys to pay a little attention to this right here. I won't really go into drawing this out because it's essentially almost the same thing that we did at the previous step. A horizontal stretch slash shrink can be represented by the function y is equal to f of c of x. Now, the c being whatever term we are given, right? So f of x is basically being shrunk or stretched by c constant. Now, the rule states that when c is greater than 1, we will shrink it in a horizontal axis, right? So it gets smaller on the horizontal axis. But when c is greater than 0 but less than 1, we stretch it on a horizontal axis. It's kind of like the opposite of the vertical stretch and shrink, which when c is greater than 1, we have a stretch, and when c is less than 1 but greater than 0, we have a shrink. Okay guys, so we have now learned about non-rigid transformations, shifts, reflections, and rigid transformations, stretches, and shrinks. Now it's time we put it all together. Our new equation is gonna be y is equal to 2x squared plus 2. This should be a negative, I'm sorry. Negative 2x squared plus 2. We're gonna actually do this step by step. I will use a different color to represent each step of the transformation. Now, the first thing it says to do is to grow this equation out by 2, right? So instead of 0, 0 will still be 0, 0. Instead of negative 2, 4, we're now going to be at negative 2, 8. And instead of 2, 4, we're going to now be at 2, 8. So what do we have here? We enlarged our equation by 2. Ignore the negative for now. Next thing says, once we do this, we're going to shift our equation 2 units up. Because, well, let me actually use green for this part. In the start, we said when our constant was plus 2, we're going 2 units up. If it's minus 2, 2 units down. So we're going to move it 2 units up. 0, 0 will now be at 0, 2. 2, 8 will now be at 2, 10. That's 2 units up. And then negative 2, 8 will now be at negative 2, 10. Okay, so we have the second part of our transformation down. Okay, guys, so the next thing we have, we're actually going to use red for this, is a negative sign. This simply states that we have to take our equation and flip it down. Just make it point downwards. We're not taking this blue one, we're not taking this black one because we already did 2 transformations to it. We're actually going to take this green one and flip it so it points down. And then the next point is going to be at negative 2, negative 6. So this will be our final function right here. Ignore everything else. I know it looks a little crazy, but this red one right here is our final function. So what did we do to this equation? First, we made it bigger, 2 times bigger. Then we shifted it 2 units up. After doing so, we reflected it to make it point down because we had this negative sign right here. That's all, guys. I hope this was really informal and you guys learned about transformations. And yeah, go out there and transform the world.